Chapter 1 Introduction. The possibility of a mathematical study of knots was probably recognized first by C.F. Gauss. His investigations of electrodynamics, 1833, included an analytic formulation of linking number, a tool basic to knot theory, and other branches of topology. It appears that the first attempts at classification of knot types were made by a British group some 50 years later. The work of Tate, Kirkman, and Little resulted in tabulations of knots of up to tenfold knottiness in very beautiful diagrams. Their early methods were combinatorial and somewhat empirical. The unfolding of the subtleties of knotting and linking had to await the development of topology and algebraic topology pioneered by H. Poincaré around the turn of the century. In turn, knot theory provided considerable impetus for developing many important ideas in algebraic topology, group theory, and other fields. Names associated with the development of classical knot theory in the first half of the present century include M. Den, J. W. Alexander, W. Barrow, O. Schreider, E. Artin, K. Riedmeister, E. R. Van Kampen, H. Seifert, J. H. C. Whitehead, H. Teitze, R. H. Fox. Typifying the general development of the theory of its technique, the concept of knot as a polygonal curve in 3 space upon which certain moves were permitted became modernized to knot as an equivalence class of embeddings of S1 in R3 or even S to the N in S to the M. Recently, knot theory has attracted renewed interest because of great progress in higher dimensional knot theory, as well as new applications, for example, to surgery and singularity theory. Oh, good God. A. Notations and definitions. Our stock in trade will be the following spaces. R to the N equals X equals X sub 1 to X sub N, the Euclidean space of real N tuples with the usual form. The absolute value of X is the sigma X to I to the 1/2 and metric D X, Y, absolute value of X minus Y. I don't know how to read this. The natural inclusions are something. Their map means continuous function of homomorphism, and equals means homomorphism or isomorphism, asterisk, asterisk, depending, of course, on the context. No doubt. 1. Definition. A subset K of space X is a knot if K is homeomorphic with a sphere S to the P. I feel like that's not an exponent for some reason. Oh god. There's S to the P sub 1? That's too much. So it's a knot if K is homeomorphic with the sphere of the SP1. Or no, not the SP1, but the SP regular. More generally, K is a link if K is homeomorphic with a disjoint union of one or more spheres. 2 knots, or links K and K prime, are equivalent if there is a homeomorphism H such that X arrow X such that H of K equals K prime. Oh, in other words, X comma k equals x comma k prime, but as a tuple of x and k and equals x and k prime. Well, why didn't you just say so? In the case of links of two or more components, we also assign a fixed ordering of the components that require that H respect the orderings. I think H should respect the orderings, even require it. The equivalence class of a knot or link is called its knot type or link type. Seems reasonable. Unless otherwise stated, we shall always take x to be r to the n or s to the n. Great. X, r to the n or s to the n. Page 3. A, section 2. Remarks. In reading the literature, you should be aware that these definitions are not universally accepted. Some authors consider knots as embeddings, K such that SP arrow SN rather than subsets. We shall also find this convenient at times, and will use the same symbol to denote either the map K or its image K of S to the P and S to the N. There are also other stronger notions of equivalence which appear in the literature. Map equivalence, oriented equivalence, ambient isotopy? Isotopy. Yeah, so that's great. Homotopy is called an ambient isotopy if identity thingy homomorphism, sure. Remark. One may also require everything be piecewise linear, or PL, or C to the infinite. I feel like that's a very spiritual statement, because we should require everything to be piecewise linear, or just to C to the infinite. I don't know what that means, but I kind of like it. Our point of view will be to work in the topological category whenever possible. But to avoid pathological complications, we will often restrict attention to the PL, piecewise linear category. The C to the infinity category will be largely ignored, but the reader is advised that the C to the infinity knot theory is different from PL in several important respects. For example, Heflige in 1962 describes an S to the 3 and S to the 6, which is topologically and PL, but not differentiably equivalent to the standard one. Great. Section B. Some examples of linking. Everyone is familiar with plenty of non-equivalent knots for p equals 1 and n equals 3, but to prove they are so takes some work. It is easier to detect linking, so we begin with some examples for a taste of what is to come, which can be handled without special machinery. We need only the well-known theorem that the identity map ID such that S to the n arrow S to the n is not homotopic to a consistent map. 1. Example. Two equivalent links of SO union SO, I think that's union in S1. So there's a circle with two X's and two dots, and then there's a circle with two X's and two dots. But two of them are on the same side on the second one. Great. Example 2. There's a sphere that's cut, is that laterally, with the dot on the top and the dot on the bottom, and some very excellent shadowing from this, 1976. But in this case, we do the slice on that side instead of in between the dots. So I guess parallel to the, instead of perpendicular to the line formed by the two dots. Example 3. There are two circles that appear to be doing that, and there are two circles that appear to be doing that. Example 4. Well, oh, I see. Are we in a dimension? So our dimension is over there and over there. And that's, is that like real numbers? Plus 1? P? Infinity? There's SP. There's P. This is a generalization of the first 3 examples. Consider for the second link, take the same S to the Q, but let the S to the P be a sphere which does not enclose the origin. Note that in the second link, the can be shrunk to a point in the thing. We show that this is not the case for the first link, hence the links are inequivalent. To see this, note that the thing equals the other thing and define a retraction, R such that the thing times the other thing, some other thing, by the formula, a formula. If there were homotopy, H sub t to the thing from the inclusion of the constant map, this does not make any sense to me. The next example is a refinement of this due to Zeeman in 1960. It is best described using the notion of the join of two spaces. Then it looks like we have exercises up to 9, and then we begin chapter 2.